Okay, so we looked at this thing and said, yeah, this is a fascination for the, these kinds of relationships are a fascination for the electrical engineers, and we're not worried about digesting all of this, but just to put our crystallographic efforts in some perspective with respect to this scheme. One of the things we want to talk about a bit today is the difference between continuous and discrete Fourier transforms. So if we look up in this corner about the Fourier series, so we have some function f, which is given by Fourier transformation of this function big X, all right? And that's set out as discrete. It sums over an index, an integer index h. If we do continuous transformation, then we're worried about things like integrating over the variables here. And so that's what we're dealing with. On the one hand, to get the density, we're looking at, to transform the density, we're looking at a continuous transformation. We want to integrate over the density, which is generally a continuous function in the unit cell. But when we're concerned with structure factors, we're concerned with these triples of integers, so we're talking about discrete Fourier transformation. So that all falls within this scheme of things, where principally the engineers are concerned with their two spaces are not reciprocal space and crystal space, or diffraction space and crystal space. Their spaces are time and frequency, okay, which are also reciprocally related. You know that units of frequency, when you tune in the radio, you're worried about, say, kilohertz, and that's reciprocal time, 1/seconds. So we want to see how Fourier transformation of some simple waveforms go. So we can imagine we're looking at some kind of density, electron density distribution, and want to transform it to get our structure factor set, for example. So we'll look at some simple cases like the sine wave, a square wave, triangle wave, and sawtooth wave. And a bunch of them are summarized here, giving the expressions for the Fourier series that represents these functions. So on the right, we have the Fourier series that represents the transformation of these functions on the left. So we'll look at a couple more closely. So if we're looking at this square wave function or top hat function, this is a simple function in which if this along this time axis, so we too are talking about time and frequency for the moment. So this is a simple function where the function is equal to pi. So this length from here to here is pi, and that height is also pi. So the function is equal to pi if the time variable is in the range 0 to pi. So in this range 0 to pi, the function is equal to pi. But if we're beyond pi, if we're greater than pi, in this range from pi to 2 pi, then the function goes negative, so its value is negative pi. So that's this simple square wave, or sometimes people call it top hat function. And its Fourier series representation, a sine series in this case, because this is an odd function, just like the sine function. So if we do an infinite series in sines of frequency times time, the harmonic series, 3 times so it's all the odd harmonics, the even ones go away. And then this plot on the right is a tabulation, a plot of those corresponding frequencies, the Fourier coefficients that correspond to these several frequencies. So here we get the odd orders, 1, 3, 5, and so on. Similarly, for the triangle function here. It's got a Fourier series representation in terms of cosines. You see it starts at 0, has its maximum value, then like the cosine goes negative and then back. So there's one period from here to there. So it's behaving, its maximum minimum behaviors are like the cosine function. So that then gets a cosine series, and here it's written out a little more clearly. Here it gets a cosine series where the harmonics are the odd order harmonics, 3, 1, 3, 5, 7, and then these coefficients are the reciprocals of the squares of those harmonic multipliers. So 1 over 3 squared, 1 over 5 squared, and so it goes. For a sawtooth function like this one, a similar kind of thing. So this one is behaving, as you see, like a sine function. So it increases, then falls to a node, and then, okay, so there's one period from here to here. Kind of like a sine function, right? So this is a sine series expansion, and here are the corresponding frequencies, but all the orders occur. Right?
Can you explain what's being plotted in the bottom graphs there?
Okay, what is being plotted in the bottom graphs there, this is like the magnitude of the coefficient. So 2 over pi times 1/2 here, so we get pi. So for this second order one, that's proportional to pi. We get, okay? So these would be the Fourier coefficients plotted out. And they're in units of frequency, whereas the function of interest is in units of time.
So the magnitude of those bars would be the frequencies of the sine waves that sum to form the time function.
Right. Right.
Is that right?
So we would combine a sine wave with a sine, a second harmonic, a third harmonic, and so on, with these coefficients, 1/2, a third, and so on, all multiplied by 2 over pi.
Frequency is on the x-axis. The height.
At the bottom here.
Okay, sorry, yeah.
Okay, vertical is like the amplitude and frequency on the horizontal axis. Sorry. So we have a couple, I think I have a couple of little movies that illustrate this, if I can make the movie. I think this one is a movie. There. Oh, I skipped over the sine one. But what you can see is, so we're trying to model this square wave function, and what's plotted here is a sine function. So now if we start, so in effect, the black curve is this first term, right? And the red square wave function would be the sum over the whole series. So what the movie is going to show is the addition of higher harmonics. So as you add higher and higher harmonics, you get to a better and better approximation to the square wave, summing over these sine function harmonics. But there's always this little bit of fringe here, this wiggling at the corners. So I don't know how many terms the movie sums over, but you need really infinitely many terms to get around the little wiggles. But you can see, I've forgotten if I read, okay, here, 25. So it sums out to the 25th harmonic, but there's still some jiggling, and if you want to go to the 100th harmonic, there would be less jiggling at those corners. You get a better and better approximation to the square wave function. Okay. Next. So here we have this like a sawtooth function. So it's also a sine series. Okay? So it starts out at zero, like the sine function, rises to its maximum, falls to its minimum, and back to zero. So as we add higher harmonics, come back.
So you got to mouse over the bottom image.
Yeah, okay. There we go. So we start with a sine function and we'll add higher harmonics of the sine. Wait, come on. There. So it gets to be, I don't know how many orders that went out to, but it gets to be a better and better approximation to this sawtooth function. All right. It's just a static illustration of approximating the square. There's another approximation of the square wave with just 1 through 5 orders. And here we have a nice movie that was on one of these wiki pages. So we're worried about, again, approximating a square wave. It's a common exercise in all of this Fourier analysis kind of mathematics. So, oh. This is a slow action movie. So now it's decomposed into all of those trigonometric components, sine and cosine terms indicated by the blue curves. Now whoever plots a perspective. So we see all those Fourier components, the sinusoidal waves that approximated so there's the Fourier transform, often indicated with a hat, and there's the function we were seeking to model, this square root like function. Okay, so that's a composite of them. And you see that very interesting kinds of functions can be approximated in this way. So here we're getting this kind of sine x over x like wave pulse, but it too can be approximated by a series of sinusoidal components. But the important point here is that these components are each relatively shifted in phase. Right? So that dashed line going back, okay, that's going through the middle maximum in all of those component sinusoidal waves, and hence we get the spike in the red curve. But the other curves are in and out of phase, so that they get canceled. We get almost nothing outside the limited range of the spike function, the sine x. The general form of that kind of function is sine x over x. And I think that's, the movie hour is over now. We've looked at this before, but just to remind ourselves of the centrality of this Fourier transform relationship in crystallography, the relationship between the crystal structure factors, and we remind ourselves that in general they are complex valued and most commonly represented as amplitude times e to the I phase. And I think we also talked about this last time. This is the mechanics of how you create the Fourier transform. If we have a set of structure factors, amplitudes and phases like this, where FHKL, this notation represents amplitude and phase together, then we sum over essentially sum over the Miller indices of the planes that correspond to scattering with this amplitude and phase. Okay, we get the electron density. So the scheme is multiply by this complex exponential, the so-called kernel of the Fourier transformation. Right? There are going to be a whole series of these terms. with different HKL, so they're in principle infinitely many terms. So we multiply by the kernel, but we have adopted the convention that the kernel for the electron density representation, we will use the negative sign in the exponent. These two must be of opposite, these two exponents must be of opposite sign. We take the convention that for the density, we put the negative sign in the exponent of the kernel. And similarly, so we multiply by the kernel and then sum over all the structure factors. Okay? And to make it be a density, we divide by the volume of the unit cell. So we're going to get something like electrons per cubic angstrom or cubic nanometer or whatever units you're using. And then to use the Fourier representation to get the structure factor values from a known or given electron density distribution, even if it's only an approximate one. Again, we multiply by the kernel, this time with the positive sign in the exponent, and then sum. But in this case, since the electron density function is continuous, whereas the structure factors just populate the reciprocal space at the reciprocal lattice points, since the electron density distribution is continuous, we perform an integration. These two expressions, which are the complements one of the other in this dual of spaces, XYZ space and HKL space, or crystal space and diffraction space. When we apply to these the properties that we will develop in a little bit, so-called Friedel's law, that reflections HKL and negative H, negative K, negative L have the same amplitude, but phases of opposite algebraic sign. Then the expressions get simplified a bit. We can replace the continuous electron density distribution in the unit cell by this set of structure factors, one for each atom, right? Where this is taking essentially the electron density distribution of the atom and computing a net scattering power for that collection of electrons that constitutes the electron density distribution for atom A. So we can move from a continuous representation, an integration over a continuous function, to a sum over a finite function, one term for each atom. So there's an atomic scattering factor for atom A. There's the transformation kernel, and that will then allow us to calculate amplitude and phase for the HKL reflection. And similarly, the electron density distribution, things simplify there. We don't have to worry about complex exponential. Since these properties hold, then applying those properties to this complex exponential, we end up getting just the cosine terms. Okay? The cosine, and it's, so the cosine of phi, that's real valued, minus 2 pi times hx plus ky plus lz. So this indicates, as we'll see in a minute, that the electron density distribution is real valued, as we expect it should be. Physically, we expect it should be a real valued function, so and so many electrons per cubic angstrom at such and such a point xyz, even though the structure factors are complex valued, amplitude and phase. So we'll look a little more detail in a little bit about how that comes out, how the basic principles of what we have in hand show us that that's true. Now this is just an adaptation to a different and more efficient notation. So the same information as on the previous slide, same fundamental theorem. So here the structure factor as an integral over the electron density, where instead of xyz, we just put a vector, a real space vector whose components are x, y, and z. Right? And then we integrate over the volume of the unit cell. All right? It's a three-dimensional, it's actually a triple integral. When we integrate over volume, it's a triple integral over x, y, z, but we have this more compact and efficient notation. And that can be rewritten as we saw before, a sum, instead of integrating over the unit cell, we can sum over the n atoms in the unit cell, each one with its appropriate scattering power, scattering factor. Okay. And then similarly for the electron density distribution, it's an in principle infinite sum of the this complex number, in general complex, f of h is amplitude and phase, times this complex number. So in the electron density sum, we have a product of complex numbers. And it turns out because these complex numbers that represent the crystal structure factors have this property of equal amplitude and opposite phases of opposite sign for the reflection and its anti-reflection, then this comes down to a cosine sum. So again, a real amplitude and no more i's in this argument of the cosine. So the position vector in crystal space is a sum over the three components times each component times a unit cell translation. So x times a, y, and so on, so on. X, y, and z range from values of 0 to 1 over the unit cell. And a, b, and c are whatever they are for this crystal of interest. So R is a vector in a real three-dimensional space. Each component is a number is a real number, and the volume of the unit cell is given by this so-called triple product: A dot times the cross product B cross C. So there we are, the coordinates in crystal space. Similarly, for the coordinates in reciprocal space, the reciprocal lattice vector is HKL, those integers, times each one times the appropriate reciprocal lattice repeat, or basis vector, A star, B star, C star. And similarly, each of those, A star, B star, C star, are given by this kind of form. A star is equal to B cross C over this unit cell volume. B star is equal to C cross A over the unit cell volume, and C star similarly. So this is a more compact and useful notation for manipulating around expressions that have to do with the reciprocal lattice vector. And the length of each reciprocal lattice vector is, according to the Bragg law, given by twice sine of the scattering angle for this reflection divided by lambda. An interesting property of A star, B star, C star with respect to A, B, C, so the basis vectors in reciprocal space, the basis vectors in crystal space, and the basis vectors in reciprocal space, have this property. This is what, for example, J. Willard Gibbs figured out and promulgated, that if we take the reciprocal space basis vector and multiply it, dot it into the corresponding real space basis vector, okay, then we get the result, this Kronecker delta again. That is, if A sub I and A sub j are the same, if I and j are the same, so A star dot A, then we get, or B star dot B, C star dot C, we get a null result, 0. But if they are, if I and j are equal, I just misspoke, didn't I? So if they are different, we get, if I is not equal to j, we have A star dot B or B star dot A, then we get a null result. But if the two are equal, A star dot A, B star dot B, and so on, we get unity, right? This is a property of these of the real and the complementarity, the reciprocity of the real and reciprocal lattices. And so the consequence of that is when we evaluate these expressions, the product of the H vector and the real space vectors, H dot R and so on, then because of this product, it greatly simplifies to just Hx plus Ky plus Lz. Now remember, H, K, and L are integers, positive or negative, or even zero in some cases, for particular cases. And X, Y, and Z are real values that have the range of, in the range of 0 to 1. So we get here then just a numerical result. So this is H dot R is dimensionless. And H dot R must be dimensionless because it appears in all these expressions for a cosine or exponential function, must be dimensionless because those functions must have dimensionless arguments. So when we think about cosines and sines, we may be thinking in terms of angles and degrees, but in fact, mathematically, those functions are defined on the basis of radian measure, and radian measure is dimensionless. 1 radian is the angle such that on a unit circle, the length of the arc that that angle intercepts is equal to the length of the radius. Okay. And just to remind you from what you learned in trigonometry. So we have this more compact, handier notation, because if we get into doing more and more structure factor algebra, it gets clumsy to be constantly dealing with separate HKL and separate XYZ. Okay, so both the structure factors and the electron density can be represented by cosine and sine summations. So the electron density, our whole point in developing the notion of the Fourier series was that an infinite Fourier series of cosine and sine terms sums to give the electron density. But if we consider the structure factors, it's not an infinite series, it's not an infinite sum of cosine and sine, but it's a sum over each of the n atoms in the unit cell, each atom represented by its own composite scattering factor, all right? Cosine plus I sine. Okay? So the complex exponential e to the I phi is cosine phi plus I sine phi. Okay? So now we notice that this part of it, so we can break this sum into two sums, right? The sum over the cosine terms, the sum over the sine terms. So let's represent the sum over the cosine terms by the symbol A, and that over the sine terms by the symbol B, so that the structure factor is this complex number, A plus IB, where A and B represent the two parts of this sum over the n atoms. The other way to write the complex number is as amplitude and phase. The amplitude, the length of the amplitude is given by the square root of the sum of the squares of the A and B part, okay? And the phase corresponding to that is given by the arctangent of the B part over the A part, okay? And the other way to write the square of the structure factor, the square of the structure factor amplitude, is the complex conjugate times the complex conjugate of FH times FH, right? So in terms of the A's and B's, that's this product. In terms of the complex exponentials, it's this product. But in either way, this is the way we write the square of a complex number. We actually square its amplitude. So we have a cosine, and we have an Euler function, cosine and sine representation for the crystal structure factors. We have a Fourier representation in cosine and sine terms in an infinite series to represent the density. So it turns out, just as we compute the structure factor, as we saw on the last slide, as a sum over the n atoms of the unit cell, each atom represented by its scattering power, scattering factor, so also we can represent the electron density as a sum over the atoms of the unit cell. That is, we can say that for each atom has its own electron density distribution, right? And then we position each of those atoms at the atomic coordinates for the atom of interest. So general position in the unit cell, R, and that atomic position, R sub A. Right? And this delta function, this is not the Kronecker delta now, this is a delta function about which we'll say some more later, maybe. But in effect, what it does is just zero everything that's not at R sub A. So we get a single component for atom A of its atomic electron density distribution positioned at its position in the unit cell. Right? We consider the atoms one by one, and in each of those considerations, zero the other atoms, and then sum them. Okay? So the structure factor is the Fourier transform of the density. We go through this, okay? We replace the density by this expression, okay? That's down here. And then it turns out that what this comes to is the Fourier inverse of this delta function, a function which has very interesting properties that we'll perhaps learn more about later, and the Fourier inverse of the atomic electron density distribution. So just as the structure factor is the Fourier transform of the unit cell electron density distribution, the atomic scattering factor is, that's this first factor here, the atomic scattering factor, denoted F sub A, is the Fourier transform or Fourier inverse of the atomic electron density distribution. So this is the way we get from sum over these cosine and sine series to sum over the atoms. Certainly there's an atomic representation just summing over the atoms in the unit cell, each at their appropriate position to give the unit cell density. And here we see how we sum over the atoms of the unit cell to get the crystal structure factor. Okay. So I pointed out, I pointed out before that these various simplifications of the expressions for the structure factor and the electron density come about because the structure factors have this property, that for a reflection HKL and a reflection minus H minus K minus L, the amplitudes are the same and the phases differ by algebraic sign. So where does that come from? If we go back to our basics, this is Friedel's law. It was noticed by Georges Friedel early on, almost as soon as X-ray diffraction patterns were discovered. He was able to see that they are essentially centrosymmetric. So there's an origin of reciprocal space, and anything that's on one side of the origin at position HKL is equal to what's over there in intensity. Intensity HKL is going to be equal to the intensity minus K of minus K, minus H minus K minus L. Okay? So there's Friedel's law. It comes about in terms of the basic expressions we're using. We can write down the structure factor for the plus H reflection. First, we can write it as a triple integral over the unit cell electron density distribution, or as a finite sum over the n atoms of the unit cell. Okay. Similarly, for the negative H reflection, we have the exactly analogous expressions, but with the H replaced by negative H, okay, which is the same as saying I is replaced by negative I, right? So we have this and this. And similarly, we do the same thing in terms of the atomic representation. We replace H by minus H, do the same thing in the exponent here, and that's equivalent to replacing I by the negative of I. So that the structure factor for negative H, negative K, negative L is the complex conjugate of the reflection for the structure factor for positive H, positive K, positive L. And we can consider that we're modeling our atoms in the unit cell to get our scattering factors as spherical atoms. So that means that about the nucleus of the atom, the electron density distribution is centrosymmetric, same on one side as on the opposite side for a spherical atom. And that means that the atomic scattering factors for that atom are the same for the negative H direction as the positive H direction. So there's just the one scattering factor representing the atom A. We don't need to distinguish in the scattering factor between plus H and minus H. So what's the implication here? That the structure factor and negative and positive are complex conjugates of one another. When we write that down in terms of amplitude and phase on each side, the implication is, okay, the amplitudes are equal, the phases are of opposite sign. So if this guy equals this guy, okay, fine, equal amplitudes, that means that e to the I phi of minus H must equal e to the minus I phi of plus H, and that means that these phi's must be of opposite algebraic sign. Friedell's law. In some very interesting cases, there are small deviations from Friedell's law. That's so-called anomalous scattering, which is a powerful handle for getting at estimates of the phases. But that comes up later on in the course. That will occur. Let's see. Yes, okay. So Friedell's law holds if the atomic scattering factors are real valued, which we assumed on the previous slide, and that they are even functions, that the scattering factors on one side of the atomic nucleus are the same, the atomic scattering factor on one side of the atomic nucleus is the same as on the opposite side, okay? And that's true if the frequency of the X-rays, or the radiation that we're using, is much larger than any natural frequency of absorption for the atoms in the crystal. That's very frequently the case, but it's not without exception. And when there is an exception, the differences are small. So that's the condition for Friedell's law to hold. Right? We're measuring at a frequency far from any absorption edge of the crystal, far from any natural absorption frequency of the crystal. We don't need to worry about any departures from spherical atomic electron density distributions or about a complex valued Debye-Waller factors. We'll see the Debye-Waller factor either, but basically it's the factor that allows for the fact that the atoms are smeared a bit because they're in constant thermal agitation. Or furthermore, in protein crystals, there can be a disordered arrangement of atoms, so that's in effect another way that they're smeared. They're either smeared by disorder or by thermal vibration. Even at the zero of temperature, there's some thermal vibration because the harmonic oscillator, the quantum solution for a harmonic oscillator has the so-called 0 point energy. But these latter two are very small effects with respect to macromolecular crystallography. Okay, so there's a consequence, a significant consequence, practical consequence of Friedell's law. So we say if we consider a case where the unit cell scattering density distribution, the electron density distribution, is centrosymmetric about the unit cell origin. So not only centrosymmetric about the nucleus in the case of atomic electron density, but here we're considering a centrosymmetric unit cell distribution of the electron density. That is, rho at minus r is equal to rho at r. Now, in protein crystals, biological, in general, biological compound crystals, even if we're just talking about crystals of simple amino acids, that's not the case. right? In general, the unit cell is not centrosymmetric. But if it were, then we would say, okay, that the structure factor, if this condition holds, we replace rho of r by rho of minus r in both these places, in the exponent and in the multiplier out front. And then replacing, so if this condition holds, then we replace rho of minus r by rho of r. And here, changing the sign of r in the exponent is equivalent to changing the sign of h. Doesn't matter whether we reverse h or reverse r, we still get the one negative sign here. And indeed, we could say, well, but that's also the same as reversing the sign of I, right, as we saw before. So these conditions, if this density condition obtains and this scattering factor condition obtains, then that means that the atoms that are at positions r sub a and negative r sub a on the other side of the unit cell origin have those kinds of positions. And if we have the equality of the structure factors, plus and minus, that means equality of the phases, plus and minus, e to the I phi of negative h to the I phi of positive h. And what does that imply? Well, that means these two expressions, exponential expressions, can be equal only if the phases, phi of minus h and phi of plus h, are equal. But on the other hand, we just went through the discussion which gave us Friedel's law. It says, no, they're not equal. They're of opposite algebraic sign. Okay. So if we consider these two conditions, this one here and this one here, that can be true only if the values of phi are 0 or pi. Right? So there's a restriction on the phases. For centrosymmetric crystal structures, we only have two possibilities for the structure factor phases, 0 or pi. And what that means is e to the I phi evaluates either plus 1 or minus 1. So the crystal structure factor is just a matter of algebraic sign, plus or minus 1, times the structure factor amplitude. Now this, in biocrystallography, does not hold for the unit cell distributions of electron density. But in some special sections of the electron density, that can be true. Imagine, for example, a twofold axis going through the origin of the unit cell. If we just project the whole structure along that axis into a plane, right, then what would we have? We would have the situation that the density at the point x, y, z and the density at the point minus x minus y minus z would be the same. We project the whole structure onto, say, the xy plane or the yz plane. So there are those special zones of reflections, even for biological crystals, except if the space group is, for example, P1, but anything like with a twofold axis, or even a set of twofold axes, there are those zones in which this restriction on the phases to just a question of 0 or pi, or that is plus or minus 1, okay, multiplying the amplitude. So in the common cases that you'll encounter when we get into actually talking about biocrystal structures, a space group of P2 sub 1 or P2 in projection along those twofold axis directions, we get this effectively centrosymmetric distribution of the planar density. In the very common space group P 2 sub 1, 2 sub 1, 2 sub 1. So we have three non-intersecting twofold axes, or screw axes, in mutually perpendicular directions. Then we get three projections that have this property of centrosymmetry. So the reflections of the type HK0, 0KL, and what's the one, H0L, those three special zones of reflections that have one of the indices 0. All those reflections are restricted to being either have phase of 0 or pi, or that is sines of plus or minus 1. So these phase restrictions are, have important consequences that simplify life for someone trying to figure out crystal structure, at least in favorable cases. Here is this point about the fact that complex valued structure factors still give us real valued electron densities. Okay? So we have seen that this is our home expression, so to speak, for the electron density distribution. And we can express the, in general, complex valued structure factor in this way. Okay. Then that comes down to this expression. We replace the exponential minus 2 pi I h dot r by the cosine of 2 pi I h dot r and the sine of 2 pi I h dot r, and then sum that over all the possible cases. So we rewrite the complex exponential in this way. We bring the phase, the complex, or the imaginary value phase, inside the exponential. So that means this thing now has, this sum has a sum of cosine terms, e to the I phi is cosine phi plus I sine phi, and then a sum of the imaginary trigonometric sine terms, sum of I times the sine of phi. Right? And here we're considering the case, all these h values we're concerned with are triples of integers. And if the Friedel law holds, that is the Friedel condition, that means that when you do this sum, the terms, the imaginary terms, go away, because there will be terms in plus h and terms in minus h, and we know that the sine of the negative of x is equal to the negative of the sine of x. So there will, all the sine terms, there will be pairs of them, all the SINE, trigonometric sine terms, will occur in pairs of opposite algebraic signs. So they cancel out, and we're just left with a cosine sum. So we get, and that's real value, okay? The amplitude, which is real value, times this cosine. No more i's here. So we have real valued electron density, even though we start with complex valued structure factors. So all of the underlying theory makes common sense. The density distribution, just we intuitively know, should be real value. And furthermore, we'll apply to it the condition that it should be non-negative. Okay, this, I guess we'll just finish on just the next couple slides on this point. How the algebra of these quantities, h and r, vector h and vector r, how we manipulate them, how we get the computer to manipulate them in doing all of the sums it must do. Okay, so we have our complementary pair of expressions for the density, for the structure factor. Okay? But now, if we consider the density with respect to x, y, z as real lengths, actual lengths, angstrom lengths coordinates of the unit cell. So then we write it out this way. Okay? Then this expression becomes the product of the h part. Well, we expand it, it's h, but vector h becomes h a star plus k b star plus l c star. Okay? Then that's dotted into this vector r, which is xa plus yb plus zc. Okay? So we have the basis vectors a star, b star, c star, a, b, c. Okay? If we multiply that out, okay, the x, y, z part in angstroms, okay, and we're going to integrate over that. So we're going to integrate over the length of a, or the length of x. Its minimum is 0, and its maximum value of x is a. Similarly, y is 0 to b, and so on. Okay? Now we do the integration with respect to those angstrom, actual lengths, x, y, z. So the x part is x times the crystal lattice repeat, y times the crystal lattice repeat b, and so on. Okay? Then the differentials that correspond to those quantities, x, y, z, dx, dy, dz, will be a times dx, and so on. So that the product of these three differentials for the integration is going to come down to ABC times dx, dy, dz, and you know the little x, y, z, the lowercase ones, have values from 0 to 1. The big ones, the uppercase ones, have values from 0 to A, 0 to B, and so on. And we have this property of the reciprocal and direct lattice repeats, translation vectors, okay? If we're talking about A star times A, or B star times B, or C star times, okay, that evaluates the unity. Phi and J are equal, but if they're different, if we're talking about A star dot B, A star dot C, and so on, then they go to 0. So this expression for the integration over the whole set of structure factors, HKL from negative infinity to positive infinity, that comes down to an integral. So this discrete summation, where we got the integer indices, comes down to a continuous integration over a function x, y, z. So x, y, z, lowercase, are what we refer to as fractional coordinates, and that's what gets reported everywhere in crystal structure results, in PDB, and so on, in SIF files, and so on. So it's the distinction between Fourier synthesis and structure factor calculations with angstrom coordinates or dimensionless fractional coordinates. Why do we want them to be dimensionless? Again, because they are the argument of an exponential function or arguments of cosine and sine functions. Those are functions require dimensionless arguments. These are transcendental functions, and they can't be changing their value if we're considering meters versus inches or whatever. Okay? So we've already talked about this business of continuous and discrete functions, and this is the way it elaborates too, that the differential things are differential of h a star, differential k b, and so on for this integration. So if we write those guys out, well, what does that come down to? That comes down to a star, b star, c star times dh to k dl. That is the a star, c star, b star, c star is the volume of the reciprocal cell. Then we're down to dh to k dl, okay? And h, k, and l are just integer numbers. So that means that HKL belongs to the integer space, 3 space, that the DH, DK, DL, that is a change from one value of H to the next one, K to the, it's in intervals of 1. These are the differences in integers, they're going to be differing by 1. Then we have this reciprocity condition, and now we have rewritten the crystal structure factor in terms of its amplitude and phase. Boom, we come down to this simplified expression in terms of fractional coordinates for the electron density. Again, this condition gives us that these guys reduce to 2 pi hx plus ky plus lz. Again, opposite algebraic sign in the exponents. Okay, so the last point. If we take those last two slides, which express the distinction between real angstrom or inches or centimeters or nanometers coordinates and fractional dimensionless coordinates, and apply them how does the computer deal with this practical summation over some set of structure factor amplitudes from some minimum to maximum value of h, k, and l. Okay? We, in principle, know that these should be infinite range, but in practice we know they're not. We can't measure them all the way as much as we'd like. So here we have this amplitude, and again, it comes down to the real valued density with a cosine, no i's here, right? Because the sine terms, algebraic sine terms, trigonometric sine terms went away because of their opposite algebraic sign. So now to get to compute density on a numerical grid, so we divide up space into little blocks, okay? And we want to sum over each of those blocks. We know that the range of these x, y, z values is from 0 to 1. So we've got p, q, r blocks. Right? So that's the value of p divided by the number of divisions that we make along x, the value of q divided by the number of divisions along y, and so on. So that delta x, delta y, delta z come down to this. Okay? A divided by the number of x divisions, b divided by the number of y, and so on. And there is this condition called the Shannon theorem from information theory from back in the 40s or early 50s. It was a kind of a big breakthrough realization on the part of Claude Shannon. But in our application of the Shannon principle, it means that there's, for DHKL, we will have some minimum spacing when h, k, and l are at their maximum values, okay? So that minimum spacing would be equal to lambda over twice the sine of the maximum Bragg angle. And the maximum interval size that we need then, the delta x for going out along the x-axis, delta y, delta z, okay? That is the c direction over the number of divisions. Those increments along x, y, z need to be less than or approximately equal to this minimum d spacing, interplanar spacing, or half of it. Okay? So there's this limit. There's no point in calculating this series with ever finer divisions than what we compute according to this criterion. If we make the divisions smaller, well, certainly the computer can do this summation, but it will give points in between, right? It will give a value of the density at in-between spaces, but it will add no new information. The maximum information that we can draw out of a given set of crystal structure factors with certain minimum and maximum values of h, k, and l is given by mapping the density on a grid with these grid divisions, which are less than half the minimum interplanar spacing. So that's for synthesizing the density. On the other way around, if we're concerned with calculating the structure factors, okay, from a given density that's calculated in this way and follows the Shannon criterion, we're calculating the structure factors, then we considered d spacings, DHKL, larger than whatever that minimum was, determined by the maximum Bragg angle that we could measure. And that needs to exceed twice the maximum of the delta x, delta y, or delta z. Vary in the three directions, of course. We're not talking always about cubic unit cells. Okay. So there's this going in the one direction, a Shannon criterion of a half d min, and going to the structure factor calculation, the Shannon criterion is twice the maximum of the subdivisions a over n x and b over ny and so on. So the computer now has the task of dealing with a finite problem. There may be many, many terms, many values of x, p, y, q, z, r, but they're going to be finite in number. So the computer can handle that. It doesn't have to try to worry about doing an actual integration over a continuous function, which would mean infinitely many points. Right, so this just expresses the same Shannon condition for the calculation of structure factors given a density on a numerical grid. So that we calculate an A part, which is a sum over the cosine terms. Here we have exponential 2 pi I phi, then we have cosine phi plus I sine phi. Okay, so we have a cosine sum, gives us the A's, parts of the complex value for the structure factor F, and then we have a sine sum, algebraic sine, trigonometric sine, that gives us the B parts. Okay? And we have that the magnitude of this structure factor, F, HKL, is equal to the square root of the sum of the squares of the A parts and B parts. So this is the way we actually calculate structure factors, and the way we used to do it by hand on paper and with a computing calculator. Well, we first evaluate the A parts by doing the cosine sums over all these grid points, right? And then the B parts by calculating this, all these values over the sine terms. Okay, so we have a numerical value for B, a numerical value for A, some of the squares of those two, and to get the corresponding phase, we take the arctangent, the angle whose tangent is equal to the B part divided by the A part. Now, both A and B are real numbers now. Okay, the argument of the tangent function must, and the arctangent function must be real value. And again, under the condition of Shannon sampling to limit things in a sensible way. Of course, Shannon was not concerned with electron density and crystal structure factor calculations. He was concerned with information theory, and information theory coded in terms of Fourier analysis of time and frequency in the time and frequency domain, rather than the reciprocal space and crystal space domains. But there's his law, his theorem for sampling. The maximum HKL is given by this condition on the minimum d-spacing, or maximum Bragg angle, okay, where the H represents a triple of integers. Similarly, on the density, the minimum distance between neighboring points on the grid is given by half the minimum interplanar spacing. So if we are considering endpoints in reciprocal space, let's say we make a set of measurements, a three-dimensional set of measurements of the diffraction pattern, and end up with a total of endpoints, then we would consider in real space a density that is on a grid of a total of twice that. Or considering a given grid, we have reciprocal lattice points corresponding to half that many grid points. So it's a classic paper, 1949, okay, there. And you can read the whole thing, because it's available online as a classic reprint. There's another name associated with this, Nyquist, who I think came along very shortly to walk in Shannon's footprints, but so it's really, and added considerably to information theory, considering things along these lines. So you frequently encounter either the Nyquist sampling, or Shannon-Nyquist sampling, or Nyquist-Shannon sampling. Those are the terms that you would keep popping up with if you're leafing through Wikipedia. All right, so I think this is a stopping point to say one other thing about the practical computational parts. We'll go into this next time. But another important advance was that computer scientists looked at the problem of calculating those big triple sums over HKL or over delta X, delta Y, delta Z, going from density to structure factors and vice versa, and found very efficient ways to code those into the programs for calculating those sums, the so-called fast Fourier transform. And another big advance in this respect, with respect to the fast Fourier transform, is the ability to, in crystallographic calculations, because fast Fourier transforms don't refer only to density and structure factors, any of these duals of spaces, frequency and time, whatever, energy and momentum and position, and so on. But in any event, the fast Fourier transform in the crystallographic application can be further simplified from just the basic principle of the FFT to applying symmetry to the calculations of these sums, given a crystal with a certain symmetry. And so it can be simplified for it. Hence, you are able to sit down at your bench with your laptop or bench top or whatever it is, and very rapidly compute a set of structure factors from a given density, or very rapidly map a density over some grid, and then cover it with network and so on, and get the density maps that we're all accustomed to looking at. It can be done very efficiently by means of a fast Fourier transform and applications of crystallographic symmetry in the computation of the FFT. Okay, so we'll get together again on Monday, and we'll go through this kind of business a little bit, just to see how big the efficiencies are when one switches from just brute force doing the summations, as they were written out on the previous several slides, to using the fast Fourier transform technique. Thank you all very much. Have a good weekend.